course, advanced topics in monetary economics. We're having an exciting day ahead of us because we're going to discuss this paper by Faccini, Bianchi, and Belosi in detail today. And what this paper is all about. Well, this paper is about a theory of inflation. And it differs from the type of theory that we've been considering so far in terms of what determines inflation, right? So far in this course, we had the idea that the inflation is determined by marginal cost and by the interaction between the economy and the central bank. And that the central bank can control the level of inflation by the appropriate monetary policy. And what we're going to learn today is that there is a refinement to be taken into account, namely that ultimately the level of inflation that you're observing in the economy also depends on what the fiscal policy is doing at the time when things happen in the economy. And so that is the key idea to kind of keep in mind. Okay? And the whole idea here goes back to the idea that if a government, say, cuts its taxes, there is a government budget deficit as a consequence, and then typically that budget deficit is covered in the short run by higher government debt. So the government, having a deficit, is borrowing money from financial markets, and then at some point the government has to decide whether it plans to pay back that debt or not. If it pays that debt back, it's called funded debt. So there is funding for repaying the government debt. But there can also be a setup in which the government may decide to not pay back the debt, or at least partially not pay back the debt. And that's what the authors call partially unfunded government debt. And that's the idea. So then that stability is then achieved by a mix of fiscal adjustments and monetary policy or inflation. And that's going to be the key idea. And then actually there are three models that the authors go through: an endowment economy, a two-agent economy, as well as a fully fledged estimation model with that has lots of different frictions and so forth. That's basically the idea. So we went through the motivation yesterday. There is a huge literature out there. So this is not the first paper that talks about monetary fiscal interactions. There is a huge literature going back to at least a key paper by Sargent and Wallace. I mean, that's now 45 years ago, but there's more papers that, of course, look at that. Basically, always making the point that it depends on the monetary fiscal policy configuration, what's going to happen in the economy to inflation and economic activity. So key contributors in this literature is Eric Lieber, Mike Woodford, John Cochran, and many of the other papers here. So we've seen, so to say, these types of things. And there is a buzzword for this often. I mean, not always, but one buzzword it's called the FTPL, the fiscal theory of the price level. So this is the fiscal theory of the price level. That's often, so to say, a buzzword. So, fiscal theory or as fiscal, has something to do with how the price level in an economy is determined. Then we have a set of literature that is already going into the type of ideas that there is maybe switches in between when monetary policy, when fiscal policy is more dominant or stronger or active or passive. These are things with regimes change when you can think about that. It's not once and for all that the central bank is the dominant player or the fiscal authority is the dominant player, but there could be switches. Who is stronger or more more forceful? And so those are monetary regime changes. And then we have the models that we have been studying so far. These are the business cycle theory models in Smets and Wouters and so forth. Okay. And you can think about these are the more traditional models of inflation determination, if you like. Okay. So this is the the traditional model of inflation determination, or the standard New Keynesian model. Okay? So this is the New Keynesian model, NK model, you know, with traditional inflation determination, with traditional inflation determination. Okay, right? So that paper, the paper that we're studying here, kind of attempts to fill, so to say, the connecting the dots between these three literatures. That's how you have to locate this paper. Okay? It tries to, fill these in one unified framework. Okay. So as I said, there are three different type of analysis in this paper, or three different models, and the first model that is very useful is what they call an endowment economy. So that's the very first type of model that the authors use, and they do that to build the intuition for their key result. Okay? So you can already get the key result of the paper from this super simple model. That's the basic idea. So they build this very stylized model so that they are basically able to convey what are the big takeaways from their entire paper. And then the remaining two models, the more complicated or more realistic models, are the models that are designed to, check is the key idea quantitatively relevant. So if we take the model to the data, is that key idea embedded in the theory, is this quantitatively important vis-a-vis the data? That's the key idea, right? Okay. So the model is so simple, the endowment model is so simple, it fits on this one page. That is the endowment model. Why is it called a Fisherian economy? Well, it goes back to the idea that this is a flexible prices model. It's a flexible prices model. Okay. Goes back to Irving Fisher. It's flexible prices, goes back to the famous economist in the 1930s, Irving Fisher, and it's a flexible price but monetary economy. Okay. It's a flexible prices, monetary economy. Monetary economy. Okay. And in this model, there are three type of players, or three entities, three different type of agents. There are households, then there is a government, and then there is a central bank. Okay? Those are the three type of agents in this economy. So there's households, there is a government representing fiscal policy, and then there is a central bank representing monetary policy. So let's start with the households. What are the households caring here about? So households are, in this model, are maximizing their present value utility. So they are maximizing their present value discounted utility. They are, so that's basically what it is. They're deriving consumption, out of consumption, they're deriving utility from that. So we just started with this slide. So this is the endowment economy that the authors study to build intuition about their key result. And then this, the endowment economy is called the Fisherian economy, going back to Irving Fisher, and this is a flexible prices monetary economy. And there's three players. There's households in the model, there is a fiscal authority, and then there is a monetary authority. And we were just starting to understand what the households problem is. The households, solve this problem. They don't even have uncertainty in this model, so there's no expectations operator. Notice that. So there's no uncertainty in this economy. Everything is perfect foresight. Everything is known a priori. Okay. And households maximize their present value utility subject to the budget constraint. So what is their budget constraint? Well, on the expenditure side, the households have nominal consumption expenditures. Right? So P is the price level, C is real consumption, so that is nominal consumption expenditures. then the households have to pay taxes. So PT times tau T are the nominal tax expenditures or tax payments to the government that the households have. So let's write this down. So tau is taxes. That's you. Okay. So they pay taxes to the government. And then the household can save intertemporally if it wishes to. And there is one asset that will allow the household to save intertemporally, and that asset is B. Okay, so B is an asset, and that's a one-period bond. And so if you're buying that asset today, it's going to pay you 1 unit tomorrow. Okay, so this is a one-period bond. It's going to mature in the next period. The price by which you're buying this asset is QT. So you're buying this bond at price QT. So it's a discount bond. It's a one period, and this is a one period bond, okay? And QT is the price of the bond, right? So it's the price of the bond. And you're going to buy the bond on the market, okay? Okay, so those are your nominal savings. And each unit of B pays back €1 tomorrow. Okay? And but what you are investing is less, so it's a discount bond. That's the way how to think about that. Okay? So this is nothing else than just a discount bond. So it's a one-period bond. You can also call this a discount bond. The discount bond. So tomorrow, okay, so that's the sources of income. Those are the expenditures that the household have. It can consume, it can save, and it has to pay taxes. What is now on the income side? What is the type of income that households have? Well, households going to get an endowment. Why? Notice that's not a typo. There's no subscript. The households get a constant endowment Y, and then that's in real terms, multiplied by PT. This is nominal income. So Y is endowment. So this is endowment. So think about it's a coconut tree, or it's an apple tree. And every period is delivering, you think T is years, once a year, there's going to be 100 apples coming down from that tree. That's your income. Or you have a field that you grow rice. Okay? So that's the endowment that you have. And that's your nominal income, which is the real, income, the number of potatoes, the number of coconuts, the kilograms of rice that you're harvesting every period. Notice that you don't have to work for it. Right? This is coming, so to say, this is growing in your backyard. The apple tree is growing in your backyard. No matter what, it's going to grow apples. That's the thing. Now later on, of course, this paper has two other models where they are going to endogenize Y. Where Y is going to be a so-called production economy, where you have to put in labor and capital to produce. But it's enough to get the key idea of the paper by this. Alright, so that's your income. And then the other income that you have is your financial income. So this is the payback of the bond you purchased in the previous period. That is the financial, so to say, assets that you're going to do. So, in other words, what you're going to see is that what is the implied rate of return on your investment? Okay, what's the implied rate of return on your investment? Well, if this is a discount bond, the return is inversely related to the price of the asset. That's the idea. So QT is the price of the asset, RNT is the rate of return of the asset, and they are inversely related. So let's maybe go through a very simple example on the one-period bond. Okay, so this is the one-period discount bond. And with the discount bond, we have this standard feature that if you put, if you put the price Q on the x-axis, and you put the nominal rate of return, R and T, on the y-axis, you're going to have this inverse relationship. That is, the higher the price, the lower is the rate of return. The higher the price you're paying for this discount bond, the lower is going to be the rate of return. And then vice versa, the lower the price that you're paying for this bond, the higher is your implied rate of return. So we have this inverse relationship between the bond and the implied rate of return. That is basically it. Now we can go one step further, and we could just consider this. Let's have an example and think about. Suppose you're buying this bond at a price Q of say 1/2. Okay? So suppose, as an example, QT is equal to 1/2. Okay? So that is, you're paying 50 cents today, and that bond is going to pay $1 tomorrow. Okay? That's the whole idea of this discount bond, right? If you're paying 50 cents to buy this bond, and that bond is going to pay back $1 tomorrow. So then let's calculate the implied rate of return. Okay? So what is the rate of return with that type of environment? So the rate of return can be then calculated as follows. The rate of return, what is that? Well, it's your expenditures, it's the payback that you're going to get minus what you paid today. So what is the way to calculate that is you are going into using this equation. This is what you paid, and this is that's what's going to be paid to you tomorrow. So we're going to calculate that as BT is what will be paid to you tomorrow. Okay. This is the amount of cash coming to you from this investment, and then you have to subtract how much you paid for that investment in the previous period. Okay. So you paid QT minus 1 times BT minus 1 in the previous period for that investment. And then, of course, to express this in percent, you're going to divide this by QT minus 1 times BT minus 1. Right? So that's the rate of return implied by your investment. Now suppose you just bought an asset, that bond that pays you 1 unit. So suppose this is all equal to 1. So you just bought a bond that pays you $1. Okay? So now with QT minus 1 equal to 1/2, and say BT is equal to BT minus 1 is equal to 1, right? So you're buying a bond that pays 1 unit of currency tomorrow, and you pay 1/2 of the dollar for it, then you can plug these numbers in there, okay? And let's see what we get out of this. So we're going to get 1 minus 1/2 divided by 1/2, right? That's so to say when you plug in these numbers. So you plug in 1, 1, 1 everywhere, and 1/2 here everywhere, so then you're going to get that. So then what does this mean? It means that you have 1 minus 1/2 is 1/2 divided by 1/2. Well, that's equal to 1.
Yeah.
So that is equal to 1. So what is that? 1? What does this mean? What does this number 1 mean? Like
No added
intuitively.
value.
Go ahead.
We don't have any added value.
Can you say it again? Sorry.
The price equal to the return, so we don't have any.
Be careful.
No.
What is the rate of return?
Not the return.
What is the rate of return that you're making?
The bond we receive equal to the price, so we don't have any return.
No, you have 100% rate of return. Look, you spend half a dollar.
Sorry.
Right?
We
So
talk about
you're spending half a dollar.
Sorry,
You invest 1/2 of a dollar today, and you're going to get paid $1 as a payout. Right? That's the key idea.
Sorry. I
Misinterpreted this, right? So you're going to have the rate of return is 100%.
Yeah.
That's the idea. So if you multiply this by 100, notice the rate of return is 100 times this. That is 1 times 100. So that's equal to 100%. You made a rate of return of 100% on this investment. Because you bought an asset at price 50 cents, and you're going to sell the asset, or the asset is going to pay to you $1 in the next period. That's a 100% rate of return. That's a juicy investment.
Yep.
So that is nothing else than just R N T minus 1. That's what this is. So, sorry, it's R N T, not R N T minus 1. So this is what the authors call R N T. That's the rate of return on your financial assets. And you can see there is an inverse relationship. Now you redo the calculations, right? This is a 100% rate of return. Now you redo the calculations and you say you increase this price here, you increase this price from 1/2 to 3/4 or to 90 cents. And what you see is the higher the Q, the higher the price, the lower is going to be the rate of return. So suppose you pay 90 cents for your bond, right? Then when you pay 90 cents, then this is this is 1 minus 0.9 divided by 0.9. So then your rate of return is going to be much smaller than with the price of 1/2. So that's where this inverse relationship between the rate of return and the discount bond comes from. All right. So that's the key idea. Why in many of these models, when you have one period debt, there is this inverse relationship between the rate of return and the price of the bond. Any questions to this? All right, good. So then that's the household side. We have, I think, a pretty good understanding what this household does. The next is what the government does. And the government is a pretty simple object here. Okay? So the fiscal authority is going to issue debt. Okay? So the households are buying these bonds. And what are these bonds? It's a government bond. Okay? So the government issues this debt. So this is when you're investing in assets here in this bond, you're saving in this bond, that's the government who's going to get that. So this is a government bond in this model. So that's the nominal value of government debt in this economy. And then the government, so to say, has that as a revenue. What is the other revenue that the government has? Well, it's going to have the tax revenue. And the government uses those two revenue items to pay back the debt that it issued in the previous period. So that's the government budget constraint. So you can think about, this is again, this is not tax revenue. This is tax revenue. And this is the bond, it's the new debt that it issues. That's the new debt. And then this is the repaying the debt from the previous period. So paying back. So if Oan bought government debt in the previous period, you're going to get that paid back, by the government. And then again, there's an implicit rate of return because the rate of return is in the previous period. You paid QT minus 1, a price for that gives you $1 today. So this is a repaying of debt, pay of debt. Yeah, go ahead.
I just want to add some details in the formula for the rate of return.
Oh yeah.
Can you go back to that?
Oh sure.
Yeah. It should be, the first term should be BT minus 1.
Can you say that again?
The first term is
This one?
Yeah, no, yes, because this is the payment that you're gonna have to pay for that. The period before that to receive this one.
You're right.
Yeah, not because.
No, wait. Oh well. Okay. Let me think for 1 second.
Yeah.
Let me.
Time one.
Exactly. You're correct. You're right. It must be BT minus 1. We're talking about the same bond. You're right. Thank you very much. Okay. So we're talking about. You're right. So please here you can delete this part. Thank you, Hui. That's really good that you're so alert on this one. Okay. So what is the idea? It also must be up there. QT minus 1. So what is the idea? This is literally a piece of paper that the government hands over to you. Okay. So I go and I'm going to go on the financial market and I'm going to buy BT units of government debt. and I'm going to buy it at some price QT. So these are my nominal expenditures for this government debt. And then the next period, I'm going to get paid this, but I'm going to get that, that dollar paid back this. That's the big. So we have to compare apples with apples. You have to do that. So that in fact, we don't need to think about this being equal to 1. This can be any number, right? Because you see now the Vt minus 1 cancels out everywhere. And you see directly this inverse relationship between Q and R. Okay, so if you do that, like you cross out the V's everywhere, and then what you're going to see, right? Cross out the V's here, there, and there, and as a result, you're going to see Rn comma T is equal to 1 over Qt minus 1. Qt minus 1 over. Now there's still one little extra unsharpness now, and I think that's going to be confusing because now I'm going to write 1 over Qt minus 1, and this is RT. That's not really correct. So this must be the return in T minus 1. So to be even more precise, so this is the return, the nominal return of your investment in period T minus 1. So then that must be RT minus 1. They must have the same dating on both sides. Okay? So this is the nominal return in period T minus 1, and that's equal to 1 over Qt minus 1. Minus 1, right? Because if you cross this and that, you see you have 1 minus Qt minus 1 divided by Qt minus 1. And then you have 1 over Qt minus 1, and then this is the minus 1. So that is the key idea. Okay? So that is the key idea on this relationship. Go ahead.
So now the consistency is with the formula. So this should be like the rate of return is usually have the symbol of the little and small, not capital R, because the R one is like the gross return.
Exactly.
So that it can actually like inverse of the Q.
That's right. Okay. So this is the net rate of return. So let's put this. You guys are great. Okay. So this is the net rate of return, right? Which is and we have to get this right. I mean that's the key idea. And by doing this so carefully, we will learn something. So this is like lowercase r n comma t minus 1. Okay. That's the basic idea. So let me take that out here. Fantastic. Okay. So let's be careful with this. Be careful. Let me just let me do it this way. So the net rate of return. So the net rate of return is your investment minus. Sorry, that's the payout minus your investment divided by what you had invested. That is the net rate of return. That's the net rate of return. And with our little numerical example, the net rate of return is 100%. So that is equal to 100%. It's up here. So that. Okay, so that is equal to 100 times this object. Okay, so that's the net rate of return. And what is this? This is equal to 100%. So the net rate of return is 100% in this example. Now we can write this net rate of return by crossing out the B's here, right, as Rn comma t minus 1 as 1 divided by Qt minus 1 minus 1, right? That's an equivalent way of writing this little form. Now, the last step is then, bring this number 1 onto the other side. So now what you're going to get is you're going to get 1 plus the net rate of return is equal to the inverse of the price Qt minus 1. There we go. And so, what is 1 plus? This is the gross rate of return. This is the gross nominal return. Okay. And in the paper, the authors abbreviate this gross nominal return as Rn comma t minus 1. And that's equal to 1 over Qt minus 1. There we go. So that is this little relationship that the authors are illustrating, that the authors make use of. So thank you very much, Hui, for really, this important, details matter, and so that's really good that we are on top of all of that. Now, this is of course in period T, right? But of course it applies to every period point in time. And so this is, we have now RT minus 1 is equal to 1 over QT minus 1, but of course that formula holds for R and T as 1 over QT, and R and T plus 1 is 1 over QT plus 1. So this was now just done on investment on the bond that you didn't invest in the last period. You could have done this equally well in this period. Okay. Any questions? That's the nature of a discount bond. Okay. Now, so that's and you see this tight connection that the fiscal authority issues this debt, and the households are going to buy that debt to save. So that's the. So what else do we have here? Okay. We have the central bank, right? So this is the central bank. What does the central bank do? Well, again, this is the gross rate of nominal return. Okay. So the central bank controls the rate of return. I mean, not controls. I shouldn't say that. The central bank tries to control the nominal rate of return in this economy, which coincides with the short-run rate on government bonds. So there is a short-term nominal interest rate that in equilibrium is going to be equal to the inverse of the price of the government bond. So there is no short-term versus long-term government debt. There is no 1 year or 2 year or 30-year government debt. This is all 1/4 government debt. You can, of course, extend this model to have like longer maturities, but this is a short maturity type setup. So the central bank follows nothing else than just a type of a Taylor feedback. It stabilizes the nominal interest rate relative to its steady state as a function of inflation in deviations from the central bank target. So when the inflation rate is high, the central bank tries to increase the nominal interest rate, and so forth. So it's a standard Taylor feedback rule. So R is the steady state. This is the steady state. And there's one key parameter that I want to highlight right away, which is this phi. Okay. So this phi here, here. There. So there's this one important parameter, phi, that is going to be one of the key parameters of the bond. And that phi is controlling how strongly the central bank chooses to change the interest rate when inflation is going to change. So when phi is large, like that's a big number, then a small deviation of the inflation is going to create big changes in the nominal interest rate. But you can also think about phi is equal to 0. Then, whatever inflation is, the central bank is not going to do anything. It's just going to keep the nominal interest rate at its steady state. So phi is going to be a super important parameter. All right. Finally, there is this fiscal rule, right? There's the government, having this fiscal rule in the sense that the government is trying to do something. And in particular, it decides about the level of taxes that in this economy have to be paid as a function of the government debt to GDP ratio. So what is SB, T minus 1? Well, let's take a look at what SBT is. SBT is the nominal value of government debt outstanding divided by nominal GDP. So this is the nominal government debt to GDP ratio. Let's write this down. This is the government debt to GDP ratio. That's what this is. It's the nominal value of government debt. That's what age is paying in this period. And given that this is the only type of debt that is outstanding then, right? We don't have these long maturities. And this is the nominal value of government debt divided by the nominal value of GDP. And then what this fiscal rule by the government is that the government, depending on a crucial parameter gamma, it's trying to you could think about interpreting this, it's trying to stabilize the government debt to GDP ratio relative to its steady state. So when the government debt to GDP ratio is high relative to the steady state, the government may raise its taxes. And the gamma is this parameter that is going to control by how much the government is going to raise taxes in response to higher government debt. So suppose for some reason there is a higher government debt, then this rule would say, depending on the value of gamma, so if gamma is a positive number, then if government debt is high, then the government is going to raise taxes by gamma. It could also be that if gamma is equal to 0, that the government, when government debt is high, it's not going to move taxes at all. So again, gamma controls by how much the government is trying to raise taxes when debt is high. Now the way this is expressed is, it's always government debt relative, from the previous period. So this is the, because this is T minus 1, so this is the nominal debt to GDP ratio in period T minus 1. So in other words, if debt yesterday was high, then the government can increase taxes, and the idea is when they increase taxes, they're going to, decline government debt going forward. If they take in more revenues, right? If they take in more revenues, they need to issue less debt in this period. That's the idea. So that's a fiscal rule, if you like, and it's designed, for gamma positive to stabilize government debt. That's the idea.
So can I ask like
Yeah.
the subscript, the xt on the left hand side is t, but on the right hand side is t minus 1.
It's T minus 1, exactly. So there's a 1 period delay, if you like, between the amount of debt. It's always the type of the stock of debt outstanding. So you think about it this way. If you plug this in here, then this becomes BT minus 1. It's from the perspective of the government budget, right? Suppose the government has to pay back a lot of debt. Right? OAN bought government debt, and OAN is going to get a lot of payback from the government. Okay? Now the government, when that thing is high, has to decide what it wants to do. Does it want to issue more debt, right, to repay this debt, or does the government want to raise taxes to repay that debt? That's the idea. So that's like, think about this is that's the total value of debt that the government has to pay to OAN here, okay? And then this fiscal rule gives you an idea of how does the government want to split it. Does it want to just raise taxes and tax the hell of its citizens to pay back the old debt? Or if it just says, no, I'm not going to move the tax, then it has to be, then there's two things. There could be, right? It has to be either issuing new debt, or as we will see, inflation and stuff like that. Okay? And then there is one more element in this fiscal rule. This is this zeta t. Okay, there's one more thing. What is this zeta t here? That is a shock. So that is a tax shock. You can interpret this as a so-called tax shock. Or is an exogenous change to taxes. So this is an exogenous change in taxes. Like for instance, right? So for instance, let's think about TEG. Suppose you have a zeta t that falls. Okay? Suppose you have a zeta t that is falling. Well, that's going to be a tax cut. Tax never going to cut. So that means the tau t is going to fall, and that's going to be the type of shock that these authors always look into. A sudden, unexpected move in zeta t. Right? A tax cut. So the government deviates from this rule. Whatever the stock of debt is today, the government cuts the taxes that the households have to pay. That's the model here. So that's a tax cut. So that is a tax cut. Tax cut. And then you see when taxes are cut, then the households have to pay fewer taxes, and then some interesting things can happen. So think about this tax cut as basically the similar thing to a monetary policy shock on the monetary side. I mean, we have the Taylor rule. There is no monetary policy shock, but we discussed this in the last couple of days that in many of the central bank Taylor rules rules, you have an exogenous shock here that indicates a monetary policy shock, a deviation by the central bank from its rule. Now there is a fiscal policy shock, where the fiscal authority deviates from its rule. That's the basic model. Yeah? Does that make sense? Okay. All right. So then there is the last equation, that's really the model. The last equation that this model has is a market clearing condition. So it's essentially saying all the output produced in this economy, what is it used for in terms of expenditures? So typically, when you go to NIPA, right, you're going to say, look, there's going to be Y units outproduced in T, and according to the National Income Product Accounting Identity, all the output produced in the economy is used for expenditures for consumption, for investment, for government consumption, and for net exports, right? So that is typically the National Income and Product Accounting Identity that many of that you have in the National Income and Product Accounts data, and that many models have. But this model is a special model. That's a super simple model in the sense of we don't have any investment in this model, so there's no physical capital. There's also no government spending, and there's no trade, and output is not varying over time. So that's what this market clearing condition is basically. So this is a really, you're going to take away a lot of elements. What's that? It is a closed economy. There's no trade, right? It's a closed economy. So it's super simple. Why? And it's of course a very simple economy, but it's instructive again to work with this simple economy to build the intuition of what the key result is. And then the purpose of the other two models in this paper is to bring back these elements, right? So to bring back investment, they have a model with capital accumulation, that's the third model. To bring back government spending, so they're going to have all these items that make output times vary. They all have that in model number 2 and model number 3. I think they don't have trade after all, so no, I know it. So trade is something that they don't have in this paper. Okay, so that's the model, folks. Any questions to the model? It's very simple, right? And the details better. So thank you again, Andy. This is very useful to kind of get this cleaned up. That this relationship, right? It's, where this relationship comes from. That's very useful that you contributed to making this tight to the side of the Okay, so then what you're going to get from this model is if you pull out your little pencil and you solve this optimization problem by households and you rewrite all these equations and you log linearize the equations, you're going to get to equations 1 to 4. So with a little bit of work, okay, you can linearize this model around its steady state. So you first do the first order conditions, you log linearize, and you're going to get to these 4 equations which summarize the model equations. So this is the equations that summarize the entire dynamics of this model. That's basically what this is. So does somebody see how to derive these equations? When you look at these equations, do you understand where those equations come from, what they resemble? So one is doing, kind of, maybe, D the same. So let me give you words what these equations mean, and then I suppose we're going to do a little in-class exercise session. We're going to derive these equations, so you're 100% on top where these equations come from. How does that sound? You want to do that? No? Yeah? So you know basically where these equations come from. So the first equation is the consumer-Euler equation, believe it or not. So this is the Euler equation. This is the consumer-Euler equation. That's the consumer-Euler equation. Yes, I'm tired today, sorry. So this is Euler equation. So it's the consumer-Euler equation. That's the consumption function of the household. Doesn't look like it, but it is it. And I'm going to convince you why. The next equation is the government budget constraint. So this is the government budget second equation. The third equation, what is that? That's the Taylor rule, right? So this is the Taylor rule. That's the third equation. And what's the fourth equation? That's the Fisker rule, right? This is the Fisker rule. So I take it, equation 3 and 4 are easy, right? Equation 1 and 2 are more complicated. That's basically the one. That's basically the one. So let's derive these equations, and let's start with the easy ones, and then we're going to go to the more complicated ones. So let's derive these equations, and they're in class. Let's do an in-class exercise here together to derive those equations. In-class exercise. Derive equations 1 to 4. So we want to make sure that everybody is able to understand where those equations are coming from. All right, so let's start with the easy ones. Okay, let's start with easy equations, and let's get started with the Taylor rule. Okay, the Taylor rule. Okay. So the original equation for the Taylor rule that we have is this one, right? So this is the Taylor rule. R n t over r is equal to phi t pi times t times pt. By the way, what is pi? Just to make sure that everybody's on board. This pi, that is pi t is the gross rate of inflation, which is the price level in t divided by the price level in t plus t minus 1. Right? That's always the same definition in many macro papers. Right? The gross rate of inflation is the ratio of the price level into goods. All right. So let's first copy this Taylor rule equation to our notepad here, and so that is the Taylor rule is R n comma t divided by the steady state level is equal to pi t divided by pi raised to the parameter phi. Right? So that's this equation. Now the first to do is we're just taking the natural logarithm on both sides of the equation. Right? So we're just going to take the natural logarithm on the left and the right. So that's going to give us the logarithm of r n comma t divided by r is equal to, and now by the magic of the logarithms, right, the exponent comes down, and then this is going to be the logarithm of pi t divided by pi. When you see an equation like that, what is the logarithm of the normal interest rate ratio? What's the logarithm of that? How can we think about that? That's right. It's the logarithm of r and t minus the logarithm of r. How did we typically call this in our course so far when we were logarithmizing stuff? Can you say it again? The growth rate? Yeah, almost. No, these are log differences, right? You can interpret them as percent deviations. So this is nothing else than just a percent deviation. So the way what we call this is often we call this just r n comma t het. That was the definition of a het variable. These are log deviations, or you can interpret them as percent deviations. So then that's equal to phi pi t het. So that's the same there, of course. So why can we write it as a percent deviation? Well, it's very simple. Let's kind of maybe take this one. By the way, right? So then the resulting equation, that's equation number 3. This is exactly equation number 3. Very straightforward. In case you're wondering, why is this tight connection there between the log ratio and this one in terms of percent deviations? Well, you can always do a little bit of a trick. You can write the logarithm of r n comma t divided by r, and that's always the same as the logarithm of, now you're going to add and subtract the number 1. So you're going to do 1 plus r n comma t over r minus 1. So you haven't changed anything. It's just you're adding and subtracting number 1. And now you can write this as the logarithm of 1 plus Rn comma t minus r divided by r. And then, what you know is, if you look at this, how would you call that? You would call that the percent deviation from steady state, right? This is a percent deviation of the nominal rate from its steady state. And that's what we typically call Rn comma t hat. It's like the definition of the percent deviation. So then we're going to have this as the logarithm of 1 plus Rn comma t hat. And there's one more step necessary. Can somebody help me here?
It's approximately
Exactly. So for small Rnt hats, if Rnt hat is small, it is approximately equal to Rn comma t hat. For small Rnt hats. So this goes back to a law of logarithms. The logarithm of any variable 1 plus x is approximately x for small x, right? That's the idea that's behind it. And now you see that you can write this, that this logarithm ratio is nothing else than just that. And we use that, in log linearizing this equation there. It's already log linear, so it's a simplification. Okay? Any questions on this? So that was the easy one. Let's go for another easy one. Okay? I would suppose. And let's go to the fiscal rule. Okay? So now we're going to do the fiscal rule. And we're just going to first copy this fiscal rule, and we're going to do the same trick on the fiscal rule. So I'm going to copy the fiscal rule next. Next is the fiscal rule. And so there we have tau t divided by tau is equal to SB comma t minus 1 over SB, all raised to the power of gamma, and then e to the zeta t. That's the fiscal rule. Just copying that rule. And now we do exactly the same type of idea. We are taking the natural logarithm on the left and on the right hand side. So then that's going to give us the logarithm of tau t divided by tau. And that's equal to, now the gamma comes down, the logarithm of SB comma t minus 1 over SB plus, because you take the logarithm on the left on the right hand side, that's a product of two things, right? And this product of two things is going to turn into a sum with the logarithms, and then you're going to have this zeta t times the logarithm of e. And then by the same ideas, right? Again you see this this ratio here, the log ratio. That's nothing else than just tau hat. So that's going to be tau t hat is equal to gamma SB comma t minus 1 hat plus, since the logarithm of e, the natural logarithm of e is 1, plus zeta t. And that is our equation number 4. That is equation number 4. There we go. Okay. That's more rewriting those equations than deriving them, but it's a good warm-up what we're going to do next. So we have an understanding of where this equation comes from. Equation number 4. Right? Are there any questions so far? Okay. So what else are we going to then do? Well, then the next thing is I have to sort of convince you that equation number 1 is the consumer-Euler equation. Okay. And for that we have to solve the household optimization problem. We have to solve that maximization problem of the household. That's, so to say, the next task that we have to do. All right. So let's do it. And the way. So how would you solve this maximization problem? So what are the choice variables? What are the things that the household is choosing? Can somebody help me? What are the choice variables of the household? Consumption, exactly, right? So the household chooses CT. Does it choose something else? BT, exactly, right? So the household chooses the level of consumption and the level of assets it wants to hold. So now what we're going to do is we're just going to write down the Lagrangian problem of this household. And then we take first order conditions. So let's write this down and let's get to the the Euler equation. So next we're going to do the Euler equation. All right. So for that we need to write the Lagrangian. L is equal to the max of the present discounted sum of utility, t equal to 0 to infinity, beta to the t. Right? So that's the first thing, and then we're going to do a square parenthesis here, right? And we're going to have the utility u of c comma t, right? And then minus, and let me use a Lagrange multiplier defined as lambda t of the constraint, right? Of the household budget constraint. So it's going to open parenthesis, and we're going to have pt times ct plus. And here I'm already going to use the substitution for Q. I'm going to use 1 over Rn. Okay? So I have 1 divided by Rn comma T and times Bt. So I have substituted here for Qt. And then we have the tax payments plus pt times the tau t, and then we have the right hand side of the budget constraint, which I'm going to pull onto the left hand side. So that's going to be minus pt times y minus the debt, the assets that you invested in the previous period paid out to you today. So that's this, and that's it. So this is the Lagrangian representation of this problem. Does that make sense? Now I want to make our lives a little easier here, and because implicitly that's what the authors assume after all. Okay? So the authors make one important assumption that I want to do here. Let's use for u of c a particular functional form, and let's have this the natural logarithm of ct. So let's use the utility function to be the logarithm. That's going to make things easier going forward. And then our choices are how much to consume and how much to invest. Okay, so those are going to be our two choices that the household is going to take. And it's choosing that for the entire sequence of time. So far, so good? Yeah? All right. So now let's take first order conditions. Which one do we want to take first? We want to take the consumption for CT. Okay, so then let's differentiate the Lagrangian with respect to CT. So what is that? Can somebody help me? What is this Lagrangian when you take the first order condition with respect to consumption? Can you say it?
U of CT minus lambda T PT.
Okay, just raise your voice. I can't quite hear what you're saying.
U prime CT.
U prime CT, exactly. And when this is log of CT, what is this? What's the derivative of log of CT with respect to CT?
C.
1 over CT, right? So so this is 1 divided by CT. It's the derivative of the utility function with respect to CT is 1 over CT. Okay, what's next?
Minus
Minus
lambda T PT.
minus lambda t
PT.
times pt. And then what do we do with this object? I'm gonna set it equal to
0.
0. Exactly, for an optimum, right? That's the idea. Okay, so that's the that's the first derivative with respect to consumption. And now we have one left over, so that's the derivative of the Lagrangian with respect to government debt, right? Or the assets. So now help me with this one. How do you write this?
Minus lambda t.
It's going to be minus lambda t
1 over RT.
1 over r n comma t. Exactly,
Plus-
right? So this is
Plus
that's-
lambda
that's
t.
this object, right?
Yeah. And plus lambda t plus 1.
Please say it again.
Plus lambda t plus 1.
Plus lambda t plus 1.
Peta. Peta. Peta.
Theta? Beta?
Beta.
Beta. Beta. Exactly, right? There we go. Okay. And then that's equal to
0.
0. There we go. Perfect. So those are all the first order conditions. Very straightforward, right, folks? No grammar here, essentially. Now I realize one thing, right? Because they make a mistake here. I realize one thing. They have forgotten the conditional expectations operator in their budget constraint. There we go. We need to put in this here.
Yeah. Expectation.
Right? Why do I say that? Right? I say that because when you look at the equilibrium equation, number one, there is an expectations operator. It's going to be very crucial going forward. So the idea is to think about this, that I take it back when I said this is perfect foresight. Right? If you go and you look at this, that's really to interpret it as a shock. So this thing can happen unexpectedly. And that's why you need to have conditional expectations. So I apologize for that. So when we are writing down this optimization problem, we have to write in this conditional expectations operator, E of 0 here.
Yeah. So E of 0 for lambda t plus 1.
That's right. So then, but of course, be careful, right? This is the conditional expectations operator from the perspective when time is equal to 0 for the entire forward length, right?
Yeah.
When we take now first order condition with respect to some t, this turns into E sub t.
Oh, yeah. Expectation
In other words, this now is going to be plus beta E sub t, not E sub 0. Because again, this is from the perspective of the entire present value time going forward from 0 to infinity. And here we take now first order conditions with respect to some period t. So that's why we're going to use the information set from at the time when we are taking these first order conditions. And that's why it's E sub t. Alrighty. So what do we next? What's the next thing?
Combine two.
The first equation.
The second. Exactly, right? So now what we're going to do is we're going to take our first order condition from for consumption and we plug it in there and we're going to plug it in here.
Yeah.
So that's the next step. So when you do that, you're going to get that the resulting equation, is going to look like this. Right? So you're going to have, first of all, you're going to have. Let me first rewrite the second equation. So let me first, before I'm going to do the substitutions, just going to rewrite this equation. So I'm going to bring the lambda t onto the left-hand side, and that's going to be equal to beta et lambda t plus 1 r n comma t, right? It's just rewriting this Euler equation or this derivative with respect to b, in standard form. And then I'm going to do the substitutions for lambda from the first equation, right? And so notice here you have 1 over pt times ct is equal to lambda t. And then I'm going to substitute for lambda t using that expression. So then you're going to get 1 divided by pt times ct is equal to beta et 1 divided by pt plus 1 ct plus 1 times R n, T. There we go. All right? Good? Excellent. So now the last last substitutions, I'm going to multiply this equation through by PT.
Mm.
Multiply that equation through by PT, and then you're going to get 1 over CT is equal to beta ET 1 over CT plus 1 times Rn comma T divided by PT plus 1 divided by PT. It's just a straightforward multiplication through. What is this? What is this object here in the basement?
Inflation.
Exactly, right? So this is equal to inflation, right? So we can write this as this is just going to be equal to pi t plus 1. So that looks like our standard Euler equation. I mean, you've seen this a million times in your studies. Is that?
The beta expectation of that and 1 over CT equal to 1 if we,
It's equal to 1. Yeah.
so we split
Yeah. Okay, that's what we get. No. I mean, just the general structure you've seen a lot. Now, good. One is ahead of us. One is ahead of us and she's already thinking further. So what now? That is what I was saying. This is standard Euler equation. And if you were to log linearize this, you will get the log linear consumption Euler equation. But it has these CT and CT plus 1 terms in it. And when you look sharply, right, the log linear equation that the alphas give us, they don't have this CT and CT plus 1 in there. How is that possible? How come when they have the equation 1, there is no consumption T and no consumption T plus 1 in there? How is this possible?
Because we have consumption smoothing.
Because we have consumption smoothing. Well, that's one possibility, right? But it's not. It's simpler than that. Very good, Ivy, right? So Ivy spotted something. Ivy spotted in these equations, the last equation, Ivy spotted the last equation.
market clearing.
This equation says CT is equal to Y. And that's gonna be incredibly helpful. But do you know where that equation comes from? How do you, why is that true? I mean, I could make things up. I'm telling you this in flowery words, and look, of course it has to be, but if something has to be the case, or whether it's actually the case, is two different things. So how would you be able? Is there a way to derive this market clearing condition? How is the market clearing condition typically derived? In 99.9% of the macro models that we're talking about in modern macroeconomics, it's always derived by adding the household budget constraint and the government budget constraint. You take the household budget constraint and you're going to add the government budget constraint to it, then you're going to get the so-called market clearing or resource constraint. Why is that? Well, think about Walras's law. If you have an economy with two markets, it's enough to describe one market, and then the other market is a residual, you make market clearing out. In other words, this is market clearing for the consumption market. It's the market clearing for the market for consumption. And once that market clears, the bond market has to clear as well. That's the basic model. We have two markets in this economy. We have the bond market and we have the consumer, or the goods market. And if we have, per Walras law, market clearing in the goods market in equilibrium, the bond market must also clear. And the way to get that result is by adding the household and the government budget constraint. All right, so let's do that. Okay? So let's convince ourselves, because you'll see this a million times in a million papers. All right. So let's derive market clearing first, and we're going to use that market clearing result to work more on the Euler equation. Okay, derive market clearing. And so that is, you're going to write the household budget. So that is PT plus times TP PT times CT plus QT times BT plus PT times tau T is equal to PT times Y plus BT minus 1. That's the household budget. And then we're going to write the government budget. The government budget is QT times BT plus PT times tau T, right? And that's equal to BT minus 1. So now the devil's always a little bit in the detail whether you're going to add those or whether you subtract those from each other. Okay? The way this works here is by subtract, and it's one is the opposite of the other. You know, so subtract now the government budget from the household budget. So that's the key idea. So we're going to subtract the government budget from the household budget. And that's going to give us PT times CT plus QT times BT plus PT times tau T. Right? So this is the left-hand side of the household budget. And we're going to subtract the left-hand side from the government budget from it. Minus QT times BT minus PT times tau T. And that's going to be equal to PT times Y plus BT minus 1 minus, right, so that's this one, minus this one. So minus BT minus 1. And then, you know, there's lots of cancellations happening next, right? So you see this one disappears against this. The taxes disappear and the debt disappears. And as a result, what you're going to get as a result of this is you're going to get that PT times CT is equal to PT times Y. So then you're going to divide by PT, and then you're going to get that famous, you know, market clearing result, CT is equal to Y. That's how you derive that. So consumption is constant. Consumption is constant in this economy. Every period, you know, what your coconut tree is giving you, you're going to eat that. Okay? And since it's not stochastic, you know, it's deterministic, Y is a constant number, your consumption will be constant. So that's an interesting result to keep in mind first. So when the government is moving around taxes, you're going to move your savings because of that. You have in this economy, because it's an endowment economy, no incentive to save, other than when the government comes and gives you more or less taxes. That's it. So if you think about this from like the household budget constraint, right? This result would say you keep your consumption constant and you're only going to move B when the government is going to move taxes. When the government gives you a tax cut, when the government cuts your taxes, what are you going to do? You're going to save those taxes. So if the government gives you a tax break, you're not going to start eating that stuff. Right? The government gives you 1,000 Vietnamese dong today and says, Dean, I have cut your taxes. I'm going to give you 100,000 Vietnamese dong today. The Vietnamese government does that. So the Vietnamese government comes and gives you, a break on the taxes. What you're going to do with that, you're not going to change your consumption. We just arrived. Consumption is going to be just equal to your endowment. You're going to eat your 10 apples a day. You eat 10 apples a day, whether the government gives you the tax break or not. So what do you do with this extra money you're getting from the government because you pay for your taxes? What do? You're going to increase your savings. That's the idea. Have you heard about this in your lives before? There's a buzzword for that. and the government gives you a tax break, you're saving those taxes because you anticipate, oh, when the government is going to pay that stuff back in the future, you will have to pay higher taxes in the future. How did you call that in your studies? You call this Ricardian equivalence. That's called Ricardian equivalence. This household sees through, hey, the government gives me a tax break today, I have to repay these taxes tomorrow. Okay? Under standard conditions. So we'll see whether that's actually going to be true or not in this model when we're going to, because that result is going to depend on what the phi and what the gamma is. But importantly, consumption is constant over time. In this endowment economy, consumption never changes. Later on with the production economy and with the estimated model, of course, consumption is going to move over time. Okay? But in this endowment setup, it's constant. Alrighty. Good. So let's now use this result in the Euler equation. Okay, so use this in the Euler equation. So then let's write the Euler equation down one more time. So then we're going to have 1 over y is equal to beta et 1 over y times Rn comma t divided by it plus 1. So I have now just substituted for ct plus 1 in the Euler equation on both sides. And I substituted for this by yt, and then of course by yt as well. Now what happens is that you see that you can strike out, you can multiply this by y, and as a result, the Euler equation that you have in this model is 1 is equal to beta et Rn comma t divided by it plus 1. That is the consumer Euler equation. That's the consumer Euler equation. Okay. And then when you log linearize this equation, right? So then you do your log linearize. How does this equation look like log linearized? When you do a first order Taylor series expansion, we're not going to do this now together here, like step by step, but you do a first order Taylor series expansion, right? And this equation is going to look like 0 is equal to et of Rn comma t hat minus pi t plus 1 hat. So that is a first order Taylor expansion or approximation. So that is the resulting equation that you're going to get from log linearizing this equation. Now you can rewrite this. You bring the interest rate to the left hand side, and so you're going to find Rn comma t hat is equal to et of pi t plus 1 hat. There we go. That is our equation number 1. There we go. So this is in the equilibrium, the equation number 1. Now I noticed something. It's of course here that right. I think when we worked on the Taylor rule, there was a little bit of it's the theme of the day. When we worked on the Taylor rule, right? I again mixed up the net rate with the gross rate. So this is of course a net rate, and the notation that the authors have is not uppercase Rn head for that, but lowercase r. It's just that's notation. It's not a mistake, but it's notation. So please change that to lowercase Rn comma t head. N doesn't mean net. N means nominal, but the way they define this R head is a lowercase Rn in their model. Okay? Upon log linearization. And so then the same is true for this expression here. So this also must be lowercase r and t head. And then here as well, This must be lowercase r and t hat. So sorry about that. It's just different notation. It's not wrong what we did. It's just different notation. And then of course up here, right, where we have this square, this should also be lowercase r and t hat. To be 100% consistent with the notation used by the authors. So you define the log ratio of uppercase r as lowercase r and t hat. Just write it. Okay, but look, let's go back then to the Euler equation. So what do we learn from this Euler equation? What does it tell us? What does this Euler equation tell us? This Euler equation tells us that what's this? What's this ratio? How do we interpret this ratio? That is it's a nominal return divided by expected inflation. What name do we typically give to that? It's the real rate of returns. It's the real rate of return. Is this real rate of return moving around in this economy? Or is this a constant? No, it cannot change. This is the ex ante real return.
Real one.
And the real return is constant. The individual elements, like inflation and interest rate, they can move around, right? So, this can go up, but immediately we need to have this going up by the same amount, right? The real rate of return is constant. Right? Because you see, this is the real rate of return, and nothing can move. The one is a number, beta is a number. So in this economy, whenever r or pi moves, the other object must move 1 to 1, because in equilibrium, the real rate of return is constant. The real rate of return is not affected by anything in this economy. So this is it's constant. The real return is constant. There we go. It's a constant. Now there's two explanations for that, why that is the case. The first one we have seen in this course last week on Tuesday. When we studied the New Keynesian model with flexible prices. We also learned that the central bank with flexible prices cannot change the real return. Right? When the central bank wishes to change the normal interest rate, expected inflation moves 1 to 1. Those were the blue lines in terms of the impulse responses on the slide deck number 2 with the New Keynesian model. That's the flexible price economy. So the real return after monetary policy shock is always constant. Let's go back to last week. Let's go back to so this is lecture. This is these are the slides leg number 1. Let's go to the impulse responses that we discussed last week on after monetary policy shock. So a change in R. And we learned with flexible prices, look, the real interest rate is constant. Cannot change. We have exactly the same result. This is how this maps into. That's why this is called a Fisherian economy here. Okay? This is called a Fisherian economy. This is the flexible price economy, in this model. Now, this model differs from the New Keynesian model that we discussed before, because here, the second reason why the real return is always constant is that consumption is constant over time. You can think about the real return is the price of consumption in 2 periods of time. The real rate of return is the price of consumption in 2 consecutive periods of time. But if consumption is constant in period t plus 1, the price should be constant as well. Why, if consumption in t is the same as consumption in t plus 1, the price is the same in period t and in period t plus 1. So the real return is the same. And only if you have consumption changing over time, you will see the real rate of return changing. So that's basically the idea. Now you can connect that to last week, right? After monetary policy shocks, the real return is constant. But of course, after technology shocks, the real return does move, okay, because of the technology shock. But in this Bianchi model, we don't have a technology shock, and that's why output is constant at all times, and so that's why consumption is constant. Any questions to this?
Would having the expected mutation there change everything? Expected rate of return is constant, or we can
Yeah, but so notice. I mean, I'm not saying that the pi can move. Pi will move around, and r will move around. So the elements of the ratio will move around in this quantity. It's just that when you compute the ratio, they are constant. And in expected value, of course, but notice that this is not expected, it's observed today. So that must mean that expected inflation must always move one-to-one with the change in the interest rate today. And that's why the ex-ante real interest rate is always going to be constant. That's just, so try to have this sinking in a little bit into your minds. That is, so to say, the key idea behind this kind of environment here. Because of consumption, and that's maybe the third reason is we have flexible prices plus consumption is constant over time. Is constant. That's the reason why the real rate is constant. When you have a flat consumption profile, why would the real, the price associated with that need to change? Okie dokie. So then we did 3/4 of the work already, right? So we did derive equation number 1 and equation 3 and 4, and then what the remaining work that we need to do now is to derive equation number 2. That's the remaining job that we still need to do. And that's a little more involved, but we'll get there. So let's do that, and we have to work on the government budget constraint. And so let's do that. So we have to derive the government budget. And let's first write this out. When you're going to write this out, you're going to get that you're going to have so what is the government budget? That's 1 divided by Rn comma t times Bt, right? Plus Pt times tau t is equal to Bt minus 1. Right? That's the government budget constraint that we have in this number. Now the first trick that we want to do now is we want to rewrite this in terms of the SB. So we want to write this in terms of this the debt to GDP ratio. So we have to rewrite this equation in terms of the debt to GDP ratio. And so the way to do this is as follows. And maybe it's good, guys, sorry about that. Maybe it's good to have this first object. Let's keep this as Qt, just as is. So let's have this Qt. So the first job that we need to do is we need to divide this equation by Pt times y, both sides, on the left and on the right hand side. That's going to be Qt times Bt divided by Pt times y plus Pt times tau t divided by Pt times y is equal to Bt minus 1 divided by Pt times y. Okay? And then you see already great things happening here, because this is nothing else than just SBT. That is equal to SB comma T. That's the nominal debt to GDP ratio. That's good. So then we have to, we can cross out those p's here. So then we're going to have tau t divided by y. And then we have a little bit of work left here on this, and then we're going to go for the break. Okay? We have a little bit of work left here. So I also want to write this as the debt to GDP ratio. I also want to write this as SB, but with a subscript t minus 1 in it. So how can I do this? Well, I need to, let me use a different color, I need to do all the standard trick in macro. You need to multiply and divide by objects, and then rewrite it. The way this works is you have to multiply by qt minus 1, and you have to divide by qt minus 1. Okay, that's the first trick. And then second, you have to multiply by pt minus 1, and you divide by pt minus 1. So you're not changing anything, right? You just keep everything as is in terms of the ratio. But then you see some magic happening here, because bt minus 1 times qt minus 1, yt pt minus 1, that object that I just circled, right, that is sbt minus 1. This is equal to sb comma t minus 1. So that's great. So then we can write this as sbt minus 1 sb comma t minus 1. That's great. And then we have a little, stuff left over here. What is this? Well, this is equal to, we have pt minus 1 divided by pt. What is this? That's inflation, right? That's 1 over pt, right? So it's 1 over pi t, right? And then we have one more thing left over. This is qt inverse, right? So this is times 1 over qt minus 1. There we go. And then we can rewrite this in one more step, right? We can then write this as sb comma t plus tau t over y is equal to sb comma t minus 1 times, well, the 1 over qt minus 1 is nothing else than just rn comma t minus 1 divided by pi t. There we go. Okay. And that is the government budget constraint, rewritten in terms of this equations. Can you say it again?
The last ratio, the view,
Yes, that's
one
the
over
exactly. Well, be careful. It's different timing, right? It's pi t minus 1 over pi t.
I know.
That's like the ex post real rate, not the ex ante real rate. Right? So we cannot, right? Because this is rt minus 1 over pi t. We could go here, right? But this is not the same timing here. Right? We need to lag this equation by 1 period. Then we could use and substitute that in. We could do that. But the authors don't like to do that. Let's try what the authors want to teach us. Let's not say go there yet in terms of further things. Now I want to just, before we go on the break now, I want to say, okay, after the break what we're going to do is we're going to log linearize this equation, and then it's going to give you equation number 2. But one thing I want to already alert you to intuitively is, if you think about, when people talk about you're going to deflate away or inflate away government debt, you can see this here with this equation already. You have inflation here, right? And inflation goes up, you're going to inflate away part of your outstanding debt. And that's basically the idea, right? That this is SBT minus 1. And if you inflate away, if inflation goes up, notice it's going to reduce the right-hand side of this equation. What's the right-hand side? This is the asset value or the market value of outstanding government debt. This is the market value of outstanding government debt in the sense of what you have to repay the people that lend you money. And if inflation is up, you're going to erode the real value of government debt. That's it. So in other words, if you gave the government yesterday 100,000 Vietnamese dong, yesterday, if inflation from yesterday to today, was huge, this 100,000 Vietnamese dong is worth nothing today, essentially. That's the idea. So even though you borrowed 100,000 dong yesterday to the Vietnamese government, if inflation is like sky high, it's a piece of cake to repay those 100,000 Vietnamese dong today. So the real value of it is going to be very small. You can already see this on this very equation. Okay. Are there any questions? And it's okay.
But I mean, but time here for the inflation is the value of Denmark is the
T minus 1. Exactly. Right? So this is exactly the idea. Like you because in period T you have to repay BT minus 1 units. Like, suppose you are an investor and I'm the Vietnamese government, and you gave me 100,000 Vietnamese dong yesterday in T minus 1. And today in period T, I need to repay you this 100,000 dong, and I will repay you those 100,000 Vietnamese dong. But of course, it depends on what is the purchasing value of those 100,000 Vietnamese dong. And if the inflation rate was 200% from yesterday to today, those 100,000 Vietnamese dong, they will not buy you many goods. That's the idea. That you're going to deflate away, or inflate away the purchasing power, you inflate away normal government debt. That's the idea. And you can see this here basically. Right? So this is 100,000 Vietnamese dong that you lend, that you borrowed, right? At the time when you pay back, this is how many goods this buys. And if the price level surges, then you can buy fewer goods for this $100,000. That's it. Okay. Other questions? Okay, you guys earned a break. So why don't we go for a break, and we're going to meet like 7 minutes after 11 o'clock. Okay, so 15 minutes, and then we're going to restart. Perfect. Okay.
Chưa vote hả? Không có
Chưa thấy vote nè. Ngành đó. Ôi chắc chị phải coi lại cái thesis của chị thấy có vẻ gượng lặt được một số cái trong này.